In this lesson, I'll show you how to use energy calculations to find linear and angular velocity. Now, if you find this question familiar, it's because this is part 2 of a video that we did earlier, and it's shown on your screen where we calculated the torque, moment of inertia, and angular acceleration. So this is part B of that video. Again, the question reads, consider a 10 kilogram solid cylindrical drum with radius 1.0 meters rotating about its cylindrical axis under the influence of a force produced by a 30 kilogram mass attached to a cord wound around the drum. I'll make an illustration of what we just read in a moment. When the 30 kilogram mass has fallen, starting from rest, through 4.0 meters, what is the linear velocity, angular velocity of the drum, and the time for this to occur? So just as before, I want to start with an illustration, and in case you did not watch that first part of the series, it looked like this. So we have a cylindrical drum, and this is what it looks like, and there is a rope or cord wound around the drum, and at the end there is a mass. So here's the mass right here, which I'll denote as capital M. What we're supposed to do is find the linear velocity and angular velocity, and the way we're going to do this is by incorporating ideas of potential energy. Given that this is hanging from a cord, it does have potential energy in it, kinetic energy, and rotational kinetic energy as a result of this drum turning. So because this mass is hanging from a cord, it has potential energy, and potential energy is calculated by taking the mass of the object times the acceleration due to gravity, which I'll denote as g, times the height at which it's hanging from. The potential energy that this object holds will go into two things: the kinetic energy as it goes down, and the energy required to rotate this drum. And to represent that mathematically, we will say that the potential energy is equal to, or it goes into, the kinetic energy as it falls down, plus the kinetic energy required to rotate this drum, which is called the rotational kinetic energy. I'll call this the translational, and the energy required to rotate it as the kinetic energy rotational. So we already know how to find the potential energy. It's this formula. So I'll replace PE with M times G times H. And the formula for kinetic energy, based on our previous lessons, is kinetic energy is equal to the half mass times velocity to the power of 2. So I'll replace this expression in for Ke sub t. So half mass times velocity to the power of 2. And to denote the rotational kinetic energy, the formula for that is half times the moment of inertia, which has its own formula. I'll represent it as I, multiplied to the angular velocity, which is denoted by the Greek letter omega raised to the power of 2. So just to reiterate, this is the kinetic energy as it goes down, and this is the kinetic energy required to rotate this drum. Let's go ahead and substitute the things that we know into this formula. So the 30 kilogram mass will be replaced in for M. I'll replace G with 9.8 meters per second squared. That's the acceleration due to gravity, and has fallen 4 meters. So I'll write down 4. And on the right side of this equation, we have half. Again, the mass is 30 kilograms. The velocity, well, we don't know what that is. In fact, by finding v, we actually found the linear velocity. So I'll just leave v the way it is, raised to the power of 2, plus half. And the moment of inertia for a cylindrical drum like this, it has a formula, a special formula, where we have I is equal to m times r to the power of 2, m being the mass, r being the radius, divided by 2. Now, depending on the shape of the object that's spinning, this formula changes. So for a cylindrical drum, it looks like that. Substituting this expression and its values, the mass of the drum is given here as 10 kilograms. So 10 kg, the radius is 1.0 meters to the power of 2 divided by 2. So that's I. And this represents the angular velocity. The angular velocity is what we're looking for. So I'll leave it the way it is, raised to the power of 2. Now, as you can see, there is some problems here. This equation has two unknowns. We have v and omega, so you can't technically solve for either of these right away. angular velocity is equal to the linear velocity, v, over the radius. This is a well-known formula and we've used it in previous videos. So I'll replace v over r in for omega. So you see this? I'll have v over r. And the good thing about this is that we can actually change r for what it actually is, which is 1.0 meters. And now we have an equation with one unknown being v, and this is solvable technically. To make matters simple for us, let's start to find out what the left side is, like actually calculate it. 30 times 9.8 times 4, and we end up with 1176 kilograms times meters squared per second squared. That's the left side. And on the right side, half times 30 kilograms is 15 kg, v to the power of 2, plus, let's multiply half, which is 0.5, times 10 times 1.0 to the power of 2 divided by 2. And this gives us 2.5. So I have 2.5 kilograms times meters squared. And over here, we can represent this as v squared over 1.0 meters to the power of 2. I've just given this power of 2 to 1.0 meters, giving us that following number. So this meters squared unit and that meters squared unit will cancel out. And given that these two terms both have a factor of v to the power of 2, they're considered like terms. So you can add 15 and 2.5 together. That's 17.5 kilograms v to the power of 2. And the left side remains the same as it was before. Now to isolate for v, we divide both sides by 17.5. So 1176 divided by 17.5. And then we will square root both sides to get rid of this power of 2, where we end up getting the linear velocity. So the square root of this number is 8.19, which I'll round to 8.20. 8.20, and the units should be meters per second. Now remember, when you do square root a number, you do get a positive and negative version, but we will only consider the positive version because the negative version doesn't make any sense in this case. So we have the linear velocity. Now we can go ahead and find the next part, which is the angular velocity. I discussed how angular velocity and linear velocity are related, and they're related using that formula. I'll take this value now of 8.2 and substitute it in for v. 8.2 meters per second divided by the radius of 1.0 meters. And what this will do if we divide these two numbers out is that this meter unit and that meter unit will cancel out, leaving us with 8.2 per second. That is the angular velocity, and normally you will see this represented with radians at the top because angular velocity deals with angles. So we put radians per second. If you like, if you don't have to put radians. And finally, to find the last bit of information that is required, which is the time that this occurs, we need to borrow information that we found in the previous lesson on angular acceleration, and this was found in the previous video, so you would actually have to watch that video to find out how this number was derived. The angular acceleration that we found was 8.4 radians per second squared. So let's go ahead and write that in. Angular acceleration is 8.4 radians per second squared, and there is a relationship between the angular velocity and angular acceleration in time, and it looks like this, where the final angular velocity is equal to the initial angular velocity, which is 0, we're told that it's at rest, plus the angular acceleration times time. Therefore, placing 8.2 in for the final, 0 plus 8.4 And make sure that you write the units down. So that's radians per second, and that's radians per second squared t. Dividing both sides by 8.4. So 8.2 divided by 8.4 should give us the time, and that is 0.98 seconds. 0.98 seconds for all of this to happen. And so there you have it. That is how to use energy calculations to find the linear and angular velocity.